Welcome to the separation of mixtures and compounds video. By the end of this video, you should be able to explain how differences in physical properties can be used to separate mixtures. You should be able to explain how distillation works. You should be able to explain how chromatography works. And you should be able to use chromatography results to determine the relative polarity of molecules in a mixture. So first, let's remind ourselves of what we mean when we're talking about mixtures and solutions. Mixtures, recall, are physical combinations of two or more pure substances. The components are not chemically combined, they're merely physically mixed. Because they're not chemically combined, they retain the properties that they had before they were mixed together. A solution is a particular type of mixture. This is a homogeneous mixture, shown here. Homogeneous mixtures have even distribution of particles. In fact, on the macroscopic level, you typically cannot visibly see one component versus the other, whereas in a heterogeneous mixture, you can usually easily see the different components. Mixtures can be separated by exploiting differences in their physical properties. Recall that since it's a physical combination, the components retain their individual properties. They don't change properties when they mix. Let's start with a straightforward example. Consider a salad, which is an example of a heterogeneous mixture. We could easily exploit the differences in physical properties of the components of this salad. For instance, tomatoes have a different color than lettuce and croutons and cucumbers. So we could easily just kind of pick apart this salad with our hands. Likewise, different particle size, using the term particle really loosely here. So there's lots of really easy ways to separate this mixture based on different physical properties of its components. A slightly more complicated example might be a mixture of iron and sand, right? Iron and sand is another heterogeneous mixture, but when you mix them together, iron retains the property of magnetism, whereas sand is not magnetic. So you can use a magnet to separate these two components of this mixture. A slightly more complicated example would be salt water, or aqueous NaCl, NaCl dissolved in water. This is an example of a solution or a heterogeneous mixture. Here you can't see the individual components, and there's no obvious way to separate the salt from the water. However, if you consider the fact that salt and water have very different boiling points, you could easily separate this mixture based on the difference in the physical property of boiling point. Water will boil at a much lower temperature than NaCl, so you heat it up until all the water boils away and you're left with the NaCl. That's essentially how our first method of mixture separation works. Distillation works by separating out the components of a mixture based on their boiling points. Recall that boiling point is directly related to the strength of IMFs. Stronger IMFs between molecules will result in higher boiling points. Weaker IMFs between molecules will result in lower boiling points. Imagine we're trying to separate a mixture of water and ethanol. Distillation works by putting the mixture into a distilling flask and then heating it up, typically using a Bunsen burner. As we heat this mixture, the ethanol will begin to vaporize first, since it has the weaker IMFs and the lower boiling point. It will travel up through the distillation apparatus, and then it will hit what we call the condenser. The condenser is surrounded by cold water. Notice there's no cold water in the tube. It's just surrounded by cold water, which then cools that vapor and turns it back into a liquid, which can then drop down into the receiving flask. Eventually, this will leave behind the water, and the ethanol will all end up in the receiving flask, since it has the lower boiling point. Another really common separation technique in chemistry is called chromatography. Chromatography separates mixtures based on the polarity differences in the components. There are three main types of chromatography that we're going to address in this video: thin layer chromatography, or TLC, paper chromatography, shown here, and column chromatography, shown here. Before we unpack these types of chromatography, let's talk a little bit about the vocabulary. There are two phases in chromatography: the stationary phase and the mobile phase. The stationary phase is the phase that doesn't move. It remains stationary. In paper chromatography, this is the paper. The paper remains stationary as you run the chromatography experiment. In thin layer chromatography, it's the TLC plate, which behaves almost identically to the paper. For all intents and purposes, paper chromatography and TLC chromatography work pretty much the same. So when I talk about paper chromatography, you can also just assume that the same goes for TLC. In column chromatography, the stationary phase is whatever components are packed into the column. Often it's a series of solids with different polarities. The mobile phase is the phase that moves. The mobile phase is typically the liquid solvent. So for instance here, this liquid solvent will move up the chromatography paper, or will move up the stationary phase. It's important to remind ourselves a little bit about polarity before we move on. Recall that polar substances will dissolve in other polar substances. This is true because they're able to form strong intermolecular forces between the solvent particles and the solute particles. These could be dipole-dipole, ion-dipole, or hydrogen bonds. Here's a picture representing the dissolving of NaCl in water, where we have ion-dipole interactions forming. Recall that the water molecules are able to attract to the different ions. Here we see the negative ends of the water molecules being attracted to the positive sodium ions, therefore forming ion-dipole interactions. Here we see the positive ends of the water molecules attracting to the negative chloride ions, forming, again, ion-dipole interactions. Hydrogen bonding is shown here, where we have a water molecule hydrogen bonding to an ethanol molecule. In this case, we would actually say the ethanol is miscible in the water. Since we typically don't say that liquids dissolve in other liquids, we say that they are miscible. Nonpolar substances, on the other hand, will dissolve in other nonpolar substances because they're able to form London dispersion forces between solute and solvent particles. An easy shorthand to remember this is like dissolves like. Polar substances will dissolve in other polar substances, nonpolar substances in nonpolar substances. Now let's think about how chromatography actually works. Imagine you take a paper towel and you stick the corner of the paper towel into a little drop of water. You would notice the drop of water would kind of get sucked up by the paper towel and move up through the paper fibers. That's exactly how chromatography works. So here's our chromatography paper. We have our solvent down here. When you put the paper in the solvent will start slowly traveling up the paper. If we put a sample of an unknown substance on the chromatography paper, as the solvent travels up the chromatography paper, as the mobile phase travels up the stationary phase, it will pull components of that mixture along with it. Depending on what the components are more attracted to, that will determine how far it moves up the paper. Components that don't move very far, like this red component here, were more attracted to the paper than to the solvent. They were not very attracted to the mobile phase, so they didn't move very far. This blue dot, on the other hand, that moved really far. This tells us it was much more attracted to the mobile phase than it was the stationary phase. So in sum, if the mobile phase, or solvent, is polar, polar molecules will travel further up the stationary phase. In this case, if we assume the solvent is polar, we can assume that the yellow component was the most polar component of the mixture because it was able to form stronger IMFs with the mobile phase. Nonpolar molecules, like this red one here, will travel less far because it was not very well attracted to the mobile phase. The flip of that is also true. If the mobile phase is nonpolar, nonpolar molecules, like the yellow one in this case, will travel further up the paper, and polar molecules will travel less far. Here's an example of a chromatograph. In this case, an unknown, right here, has been spotted at the origin. We don't know what this unknown is made of. Then we add a solvent, that's our solvent front here, and that solvent moves up the paper, carrying components of this mixture with it. We've also spotted A, B, C, and D, the things that we think might be in that mixture. Using this chromatograph, we can ask ourselves two questions. First, what are the components of the unknown? And second, which of those components is the most polar? Pause the video here and consider these questions. When you come back, I'll discuss the answers. Welcome back. What you should have determined is that this unknown contains components A, B, and C, but not D. We can tell this because you can see that the unknown had a component that traveled just the same distance as A, a component that traveled just the same distance as B, and a component that traveled just the same distance as C, but no component that traveled the same distance as D. In terms of polarity, we need to consider the solvent we're using here. Hexane looks like this. Assume that there are hydrogens on the end of each of these lines. This is a non-polar, I'm a carbon short. This is a non-polar molecule. There's no permanent dipoles here. Therefore, it will attract non-polar components of the mixture most strongly, and those components will move the most far. Therefore, we can conclude that B is the most polar because it was least attracted to the non-polar mobile phase. That brings us to the end of this video. Let's review our goals. First, we looked at how differences in physical properties can be used to separate mixtures. Then we explained how distillation works, exploiting the differences in boiling points to separate components of a mixture. Then we looked at how chromatography works, exploiting differences in polarity to separate components of a mixture. And finally, we used chromatography results to determine the relative polarity of mixtures of molecules in a mixture.